We now turn to the next topic, the orthogonality of wave functions. We consider the one-dimensional time-independent Schrödinger equation for two wave functions or eigenfunctions, psi sub n and psi sub m, with corresponding energies or eigenvalues E sub n and E sub m. The terms eigenfunction or eigenstate and eigenvalue or eigenenergy will become clear later once we recognize that the time-independent Schrödinger equation is an eigenvalue equation. It fits the definition of an eigenvalue problem. The claim is that if these two wave functions or eigenfunctions correspond to different energies, then they are orthogonal. In mathematical form, we have the expression shown here. This is the orthogonality relation in one dimension. This integral is precisely the inner product of psi sub m and psi sub n. It tells us how much one state contains the other. We will talk about it in more detail later under the framework of Hilbert space. The orthogonality condition means that the overlap integral between the two wave functions is 0. Physically, the overlap here is not the overlap of two plotted curves in the ordinary visual sense. It is a measure of how similar two quantum states are. Now let's understand the strategy of the proof. We start from the two time-independent Schrödinger equations, one for psi sub n, the other for the complex conjugate of psi sub m. Then we multiply equation star by the complex conjugate of psi sub m and equation double star by psi sub n. After that, we subtract one from the other. So the potential terms cancel out, and the remaining expression can be recognized into a form involving the energy difference, E sub n minus E sub m, on one side and a derivative structure on the other side. We end up with the expression shown here. Using this identity, which allows the left-hand side of this equation to be rewritten as a total derivative, this is the key technical step. Then integrating both sides of the above equation, we obtain the boundary term. This term must be 0 because for normalizable bound state wave functions, the normalization condition requires that the wave functions vanish as x approaches plus minus infinity. So once that boundary term vanishes, what remains is this expression. So the energy difference times the inner product of psi sub m and psi sub n must be equal to 0. Now here is the key conclusion. If E sub n is not equal to E sub m, then the factor E sub n minus E sub m is not 0. Therefore, the only way the equation can hold is if the integral is equal to 0. And this is exactly the orthogonality relation for distinct eigenfunctions. We then generalize the orthogonality relation to 3 dimensions. Instead of integrating over one coordinate x, we integrate over whole space. The orthogonality condition becomes the expression shown here at the bottom of this page. So the idea is exactly the same as in one dimension, only the notation changes to 3-dimensional space. This completes the proof in the general spatial setting used in quantum mechanics. At this point in the chapter, we are providing the orthogonality directly from the differential equation itself. Later, when we learn more operator theory, this result will appear as a special case of a much more general theorem. Now we go one step further. If we combine orthogonality with the normalization condition, then the result can be written in a very compact and elegant form as shown. where delta sub mm is the Kronecker delta. We know that when m equals n, delta sub mn equals 1, otherwise it must be 0. So this single equation contains both normalization and orthogonality at the same time. If m equals n, the integral becomes 1, which is the normalization condition. If m is not equal to n, the integral becomes 0, which is the orthogonality condition. So this is a very compact and powerful way to write the result. On the other hand, in bracket notation, which was introduced a couple of slides earlier, the same relation would be written as shown. This is the standard orthonormality condition for a set of eigenfunctions. The word orthonormal simply means orthogonal and normalized. This condition is enormously important throughout quantum mechanics. Once we have a set of orthonormal eigenfunctions, we can use them as a basis to expand more general wave functions that will later connect directly to Fourier-like expansions, matrix mechanics, and abstract vector space methods.